Hi, my name is Luke Wilson. I'm here with John Lockman. We're the co-creators of the Omnia project, a new open source community-driven framework for composing high-performance clusters for simulation and modeling, artificial intelligence, and data analytics workloads. Why is it that we created the Omnia project? Well, we think it's time for a new approach. We think that next generation research compute platforms are going to be very different than what we see today in the HPC clustered space. Instead of homogeneous designs where every cluster compute node looks exactly the same, we see a more heterogeneous architecture built on standardized building blocks, but with each building block being different, consisting of either dense compute or GPU acceleration, which comes from multiple vendors, FPGA acceleration from multiple vendors, or the use of special purpose accelerators for deep learning and other emerging workloads. We think that the way software is going to be delivered to users in the future is going to be significantly different. We've seen this enormous growth in container technology in the enterprise and cloud space. And we think that containers provide the best way for researchers and technology partners to provide optimized software to end users. And you can do it in a bare metal, maximum performance sort of way, and have the ability to use various accelerators and network interfaces. And so we think container native is going to be the way to deliver software in the next generation of high performance systems. And we need to do this because we need to embrace emerging workloads. We're not just doing simulation and modeling anymore. Much of the work done on HPC systems involves distributed or accelerated data analytics, machine learning, training and inference, or deep learning and training and inference, and a whole host of other workloads that are still emerging, still being developed, that may not fit in the existing HPC workflow. We also want to take advantage of all the great work that's happened in the enterprise and cloud service provider space to do software-defined deployment and management of clusters. Very large data centers exist in the enterprise and cloud space, and they've developed a complete tool set completely independent of the HPC space to manage these large-scale systems. And in many cases, these tool sets give new abilities that we're not used to in the high-performance computing space. And so we should be able to use those techniques to be able to build high-performance clusters that allow for rapid deployment of software-defined solutions, expansion of those solutions with additional infrastructure when it's time to grow those clusters, to be able to easily tear down short-term solutions, and to do everything using infrastructure as code practices. And so we developed the Omnia project as a way of bringing these two worlds together. The Omnia project is an open source framework for composing high performance clusters, community driven, started by Dell Technologies in partnership with Intel, but open to the entire community. We currently have a few other community members like University of Pisa, Arizona State, and Visius, and we're accepting contributions from everyone. We have contributions coming in from all over the world, whether it's academia or industry or technology partners. And you can find Omnia on GitHub today. It's at github.com/DellHPC/Omnia. Omnia doesn't really develop software. It leverages best of breed software. So Omnia is focused on the installation and configuration of existing software tools and technologies to perform certain functions. We will not reinvent the wheel if we can find a good software package, a good software project that's already doing the work that needs to be done. And so, we leverage best of breed software from all the way from the lowest layers, from bare metal provisioning using things like Cobbler to existing package management tools, existing things like software-defined networks and key value stores. For Kubernetes, we use existing load balancers, schedulers, and package managers. And then moving up the stack, we use containers as the way of delivering user-level software. And we even deploy platforms for doing deep learning and machine learning training and pipelines. And we offer two different stack opinions at this point. One of them is our simulation and modeling stack based on Slurm and Singularity. And in the simulation and modeling stack, we automatically detect and deploy accelerator drivers. So we will actually pull the PCI bus in each individual server, see what accelerators are there, and if we can support them with automatic download and installation of drivers, we will do that. We then install Singularity as the container runtime and Slurm as the workload manager. On the Kubernetes side, we have a slightly deeper stack because installing Kubernetes by itself is not entirely useful. You need to have all of the associated packages, operators, extensions, and components to make it a functional system. So in addition to automatically detecting and deploying the accelerator drivers, just like we do with the Slurm stack, we install our container runtime. Currently, that's Docker CE, but we're moving to Podman as the container runtime for Kubernetes. Install Kubernetes on top of that, add all of the various operators and extensions that make that cluster useful, such as an NFS client provisioner, MPI operator, Spark operator, so on and so forth. We then add load balance and ingress components such as Metal LB, which help to manage the IP space if you wanted to offer public services or semi-public services from your Kubernetes cluster. And then we install those user platforms on top, including Kubeflow, Polyaxon, Jupyter Hub, and coming soon, Converge.io. And this is all done using Omnia's intelligent cluster deployment approach, which is a three-step process that involves inspecting the contents of each server, looking at its current operating system, looking at the PCI bus to see what accelerator cards and network interface cards are available, and then building that manifest out for each server, which we then use to inform the installation phase, where we deploy the accelerator drivers, we deploy all the software for the particular software stack you want on your clustered solution. And then once all that software is installed, we integrate it all together. We configure all of the software packages and components. We make sure they all work nicely together so that at the end of the Omnia deployment phase, you have a fully functional cluster with all of the packages configured and all of the nodes joined together and functioning correctly. Like I mentioned before, Omnia is all open source, but if you do happen to need support, there is pro support available from Dell Technologies, currently available on Intel-based platforms until next March. After that, pro support will be available on all platforms, including AMD. And this intelligent deployment approach gives us an enormous amount of flexibility that you wouldn't get in a traditional HPC provisioning and deployment tool set. Because in a traditional HPC deployment tool like OpenHPC, you've married the deployment of the user level and cluster management software with the provisioning of the operating system. When you build out a resource pool, you end up building one cluster. And that's completely fine. If all you need in your data center is a single cluster, then that would work just fine. And Omnia can do that as well. You can use all of the resources to build a single cluster. But you don't always need that. Sometimes you need to build multiple clusters with different software packages to suit different researchers or users' needs. And so Omnia allows you to have the flexibility in your resource pool to partition up the space so that you can build logical clusters in your physical resource pool with different software stacks, different user platforms, different user sets, and then resize these resources, destroy these resources as necessary so that you can take maximum advantage of your resource pool. And the resource pool is managed by the Omnia control plane. The Omnia control plane is itself a solution deployed by Omnia. It's a self-bootstrapping process that uses Omnia to build a server or set of servers in the near future that handle all of the provisioning by doing automatic detection and configuration of servers, network, and storage using either iDRAC or PXE. And so if you have an iDRAC enterprise or data center license from Dell, it'll automatically detect that iDRAC interface and use iDRAC for doing firmware updates as well as OS provisioning. If it doesn't detect an enterprise or data center license, it'll automatically roll back to Cobbler and using PXE provisioning. And so you can seamlessly use a mix of hardware with a mix of different license enablements for the out-of-band management system, and Omnia will take care of it. The Omnia control plane also handles all of the deployment. It manages all of the creation of on-demand clusters from the Omnia resource pool, and it allows for scaling of those logical clusters. Resize those clusters on demand to better make use of the Omnia resource pool, or destroy those clusters if they're no longer needed. The Omnia control plane provides a zero-touch provisioning approach for the operating system, and then a one-touch deployment approach, since you have to pick the servers that are going to be part of that logical clustered solution. Now, traditionally on an HPC system, you would install software directly to the OS layer, and you want to have the ability to have multiple compilers, multiple MPI libraries, multiple math libraries, and so we end up with these complex hierarchies of software packages. And we have tools to help us manage these hierarchies, such as modules that allow us to change the LD library path, the path variables, and whatnot, so that we can use different versions of a software package at any given time. But these approaches don't give full flexibility in the software stack. It can sometimes be very difficult to change the underlying Python version or the underlying glibc version without affecting the underlying system itself. And you can see that this approach also requires the recompilation of an application multiple times. So we have 3 applications in this picture, A, B, and C. But we've had to build 18 different copies because we have 6 different combinations of math library, MPI library, and compiler. And we think going forward, the way to fix this problem is to switch to containers. So in a container, we can embed the MPI libraries, the math libraries, the compiler, the framework, the application, all of it inside the container, as well as the operating system image and the glibc stack. And so you can now use versions of glibc that you don't have available on your system because your system is fixed at a particular level. Say you have a Lustre file system or something like that that prevents you from upgrading the system to a newer stack. You can now contain all of that within the container. And then with a very quick one-line change in the way you compile or the way you run your code, you can use a different build environment, a different runtime environment to do whatever you need to do. This also eases the burden on the system administrator, because instead of the system administrator and a team of HPC specialists being tasked with constantly rebuilding software packages, trying to get them as optimal as possible in terms of performance on the system that they're running on, we can leave it up to the technology partners. So we can now pull our containers from Intel's One Container Registry or AMD's Infinity Hub or NVIDIA's NGC and get the most optimized version of that particular software package for the platform we need to run on. We can also pull containers from all sorts of different places, like the Xilinx marketplace if you happen to have Xilinx FPGAs, or if you like the OpenHPC environment, you can just pull an OpenHPC container directly from Quay, and that gives you the standard OpenHPC environment that you may already be used to. You can also just pull random containers from Docker Hub, Quay, or even set up your own local registry with some vetted containers that you've already defined.
All right. Well, thanks, Luke. That was a great introduction to what the Omnia framework is all about. And what we wanted to show in this talk is really how easy it is to get started and deploy these services in this control plane itself. Obviously, one of the first things that we saw in building a data center is the complexity behind provisioning all of your hardware. We wanted to make that really easy. And so I was able to actually fit it all into one slide of code. That's really just a couple of upgrades and installs of things you already have on a CentOS 8 based system. We clone our Omnia repo from the release branch. We go into the control plane directory, and we essentially just run that control plane playbook. There's a few settings you can add to it if you want to change some of the defaults, but basically it's ready out of the box to take a base CentOS 8 system and turn it into this control plane that Luke described. This control plane today is actually a standalone Kubernetes deployment on a single node that contains the cobbler instance, the AWX instance, and your DNS controller for the cluster and for your entire data center. So again, just a handful of commands and we're up and running with a provisioner that we can rack and stack nodes, and it will automatically identify systems that are plugged in onto the same network. If it's iDRAC and it sees your enterprise license, it will use OpenManage and update all of your firmware and all of that good stuff. If it doesn't find any iDRAC or enterprise licenses, we just roll back to the standard cobbler Pixie provision. Very simple, but still gets us up and running. And once I have that control plane, Now I can start to build my cluster inventories. As we were looking at earlier, you saw we have a whole data center full of compute infrastructure that may be all sorts of different hardware. And what we want to do is be able to make small logical clusters out of that hardware. Now, if you don't want to use that control plane, that's not a problem because you can actually just start right here. You already have a provisioning system that you use MOS or you use Terraform or Packer or whatever it is that you're already comfortable with. That's great. You don't even have to use the control plane. That's really just a place to get people started. If you already have systems that are set up, networked, and have names, we can just create inventory files based out of that data center infrastructure and apply a few different roles to build a cluster. So the roles that we've created here are a manager, where all of the Slurm control D and all of the Kubernetes management services live. An NFS node, which in this case is just a system with a bunch of disk in it. A login node to support our users coming in and for ingress if we're actually exporting some Kubernetes services, and then our compute services. And of course, we can just label those in large arrays, and we can say, I have hundreds or thousands of these nodes. And now I've built myself a logical cluster. I have all of the components that we normally see in a cluster. And what we can do is using the Omnia Ansible playbook, we can tell it which version of Kubernetes we want to use, which is currently 116.7 or 119.3, and if we want to use a login node or not. If we do use a login node, then we go ahead and configure a full setup of free IPA for user management with Kerberized logins and all of that goodness that comes along with that. And then again, same thing, it's a one-liner to deploy this cluster. It's just the Ansible playbook, running the omnia.yaml and passing it that inventory that we had just passed it. And so now out of my group of infrastructure, I've been able to create this logical cluster, manager, login, storage, and you can see it over here in my picture. And now that I have that infrastructure, I can deploy platforms on top of that. Again, you already saw that it can deploy a basic Slurm workload manager with Singularity, but we can also deploy full Kubernetes and packages on top of that. Things like Kubeflow are one-liner installs. Just Ansible playbook, the Kubeflow playbook that we've created, and you pass it that cluster inventory. And you'll be up and running with an interactive version of Kubeflow where you can run notebook servers, pipelines, neural architecture searches, all of the good things that you like to see inside of that machine learning software stack. And of course, because we're already detecting all of the hardware that's on your system, we can also take advantage of GPUs and FPGAs that might be on your system. Now, what about when I'm doing my traditional simulation and modeling? You heard us talk a lot about how we're not really going to install any software. We're just going to install Slurm and Singularity. And the reason for that is we do believe that the containerizing these workloads is the way of the future to deliver software. It's just easier. We can rely on our vendors to provide highly optimized kernels inside of those. And so we relieve that burden from the administrator to build all that software. And now what I want to show you is on this one system, I can say, I'm really comfortable with the Open HPC project. I really like the way that they work. I love the way that the packages and all of the libraries are provided. And so I want to use that. And so I can just create a Singularity image of that container, and I can use the MPI-CC inside of that container. And the OpenHPC, it's a GCC with MBAP 2. It's a pretty modern GCC, which again is something that I don't typically get on my host system. And then on the other side, I'm using Intel's OneAPI container, the OneAPI HPC toolkit. And that one includes the Intel compiler, the Intel MPI library, and maybe my packages depend more heavily on that. But again, just a single change in my Singularity run command allows me to use a completely different build environment. And I'm still just building an MPI code. I'm still just using MPI-CC, but I'm able to really easily swap that out as a user. And then running these jobs is just the same as nothing's really changed. Although, as we pointed out earlier, we're building these as Singularity containers. And so instead of using a MPI run in your batch script or a custom InfiniBand run script, we just use the built-in PMI2 interface from Slurm and pass that to the Singularity exec. And what that does is allows whatever MPI library is inside of the container to communicate over the PMI2 interface. And what we see there is bare metal performance while we're running containers, which is awesome. On the other end, I might want to be using things like inference servers on my Kubernetes side. And because we have both systems that are available in here, this makes it really easy to get started and deploy things like inference servers from Intel's One Container repo. We have the Helm version 3, so you can really quickly one line install things like an inference server like this from Intel. We can also do the exact same thing with containers from NVIDIA and containers from AMD's Infinity Hub. So now we're all done with that cluster. We've run our workloads. My research team has moved on to their next project. We're trying to do something new. So we want to return that hardware back into the resource pool. Again, this is a really simple operation, just using a single one-line playbook with Ansible playbooks. And here we again just pass it the cluster inventory that we had used there. And using the destroy playbook, we can quickly return all of this hardware right back into the resource pool that can now be again reused to build another logical cluster, Slurm, Kubernetes, or whatever we need for our designated workload.
And so that's the Omnia project in a nutshell. Like I said, this is not an effort that's driven just by one organization or a handful of organizations. This is a community-driven effort, and we encourage everyone to join the Omnia community. You can find Omnia on GitHub. You go to github.com/delhpc/Omnia. You can start the project, clone the repo, download the tarball, give it a try, request new features, submit a bug report. Anything you think would be useful, let us know. Or if you just want to let us know that you're using it, feel free to do that. You can also find us on Slack. We're part of the Dell Technologies HPC community Slack team. So if you go to dellhpc.org, you can join the Slack and we'll be there in the Omnia channel. You can also find us on social media. Just look for the hashtag OmniaHPC on both Twitter and LinkedIn. And we'll be talking about features, releases, blog posts, and all sorts of different stuff on there. Also, if you're using Omnia and you really like it, have your organization become a community member. It doesn't take anything to join the community. Just a request on our GitHub will allow you to join the community. You can have your logo up there. Just let us know and let the world know that you're using Omnia, you're trying it out, and you think that it's a good approach and it's something you're interested in. And with that, we'd like to thank you for your time, and we hope you enjoy the Omnia project.
Thanks, everybody.